Planetary bodies in our solar system have undergone chemical change throughout their history, where influences from pressure and temperature have altered the way in which minerals are assembled. Earth shows us that if a heat source is constant in the deep interior, then it can drive the planet to have separate layers, such as a metal-rich core, a hot and melted mantle, and a cold outer rocky crust. We call this special planet-separating process planetary differentiation, and that's just a fancy word for the splitting of layers in a planet, like slicing into the different layers of a birthday cake. Let's take a trip into Earth. We carry out our daily lives on the crust, which is the outermost layer and the top surface of Earth. Every so often, some active geologic events below our feet make their way to the surface. Although the activity deep below inside of Earth is constantly happening, only some of that activity reveals itself. Some of the most common surface activities are volcanic eruptions. Volcanoes have giant tubes, like plumbing systems, that go far down into Earth. We see this activity as lava flows, such as the volcanic activity at Kilauea in Hawaii. Achondrite meteorites are a type of meteorite that have undergone processes that appear to be similar to lava flows and crust-like surfaces. The achondrites are a rare type of meteorite that make up a very small percentage of the total meteorites, but may be revealing large-scale processes like melting, volcanic activity, and planetary differentiation. As we go deeper into Earth, we head into the main chamber, named the mantle. By volume, this makes up roughly 70% of our entire planet. It is a big melting pot of minerals and rock chemicals, where the rocks are molten and they flow like hot asphalt. The most common element in the mantle is oxygen. The oxygen that resides here is the same oxygen that you and I breathe, but melted in liquid form and bonded to silica to make up the rocks of Earth. The most common silica rock in Earth's mantle is the mineral olivine. You may be familiar with olivine when it's in a polished gem called peridot. The olivine mineral is green in color and is also rich in metals such as iron, magnesium, and sometimes nickel. Olivine is one of the most common minerals found in some meteorite types. Interestingly, there have not been any meteorites that have arrived to Earth that resemble or represent a mantle. This is what meteorite scientists call the missing mantle problem. Since Earth has drastically changed over time, we look to the chemistry and mineralogy of the meteorites in order to help us understand how Earth first formed and what type of chemistry was available for planet formation. Some meteorites have not geologically changed since the very start of our solar system. They offer mysterious clues we need in order to piece together the first few million years of our planet's forming. The material in the mantle has experienced many chemical changes over the 4.6 billion years of Earth's geologic history, but many meteorites have not changed during that time. We need meteorites to solve the mysteries of planetary formation that Earth has melted and erased. As we go down further below the mantle, we arrive to a very special layer called the D double prime layer, which is the boundary zone between Earth's outer core and the mantle. This is a transition zone where a special mineral known as perovskite occurs, and this is the only location on Earth that we know of for it. Perovskite is a calcium titanium oxide mineral and occurs as a dipyramid crystal structure. Here, closer and closer to the core, the iron becomes highly enriched in the minerals. This is where the iron-rich core of Earth interacts with the above silicate-rich mantle. The meteorites known as the pallasites are thought to represent this special zone, where the olivine-rich mantle begins to touch the iron core. Almost like raindrops, the olivine minerals fall into the liquid metal interface. Since this is so deep in Earth, geologists have a hard time understanding this part of Earth. We use the Palisite meteorites to help us understand this interaction zone. The temperature here is roughly 7,000 degrees Fahrenheit. Earth's core is our final destination. However, there are two core layers. First, the liquid outer core is what surrounds the solid inner core. So we first must swim through liquid iron and nickel. The element sulfur is in abundance here with the metals and floats along within the molten material. The immense pressure and temperatures keep the metal in a liquid fluid-like state. The electronic current flowing through the liquid metal combined with Earth's spin rotation is what creates Earth's magnetic field. The temperature is estimated to be 8,000 degrees Fahrenheit. Finally, the deepest part of our trip into Earth is to the solid ball of crystalline iron-nickel alloy located at the center of the planet. The solid metal here has only been measured by seismic waves traveling through Earth. This is an impossible place for geologists to ever access. The iron-type meteorites that arrive to Earth help tell us a story of what a planet core looks like, since we can't directly study our own core. The estimated temperature here is roughly 9,806 degrees Fahrenheit, which is close to the temperature of the surface of the Sun.